The second session will be handled by Dr. Basanta Kumar Behera. He is currently serving as an assistant professor in Polymer Engineering Department at B.S. Abdur Crescent Institute of Science and Technology. Dr. Behera sir holds a PhD in mechanical engineering with a specialization of polymer composites. He completed the degree in 2024. And also he holds a M.Tech in Polymer Science Engineering from Anna University and a professional degree in Mechanical Engineering from the Institution of Engineers, Calcutta. He has a teaching experience of more than 30 years with last 17 years in Crescent University. He taught courses like polymer processing, plastics and rubber product design, mold and die design, strength of material, engineering mechanics, etc. Recently, he has published 4 journal papers as a single author on thermoplastic polymer composites, and in a few of his papers used mechanics of composites as tool to predict the properties. So we are honored to have Dr. Behera sir with us today to share his knowledge and insights on composite mechanics. Sir, please.
Okay, Dinesh, thank you. Thank you so much for the introduction. And now this session actually will be a type of interactive type of session where we will go for actually composite mechanics. May I ask Samsad madam, actually can the participants can ask question in between?
Sure, sir, sure.
Okay. Because it will become actually more little bit actually. So participants, you are free to actually ask, actually stop me at any location, at any place, and you can have your questions. Okay. So Vanakkam, Namaskaram, and good evening to all of you. Because as Madam already said, actually around from 33 institutions actually people are there, and it is all across India actually. So all different languages are there, and those who knows he is actually Tamil, sir, actually are free to ask me in Tamil, and English will be our platform, but your own language, if you are using in between, actually is not an issue, and Hindi is not an issue for me. Okay. So, am I audible to all of the?
Yes, sir.
Whether my screen is visible? No.
Yes.
Screen
yes,
is...
Behera, you are visible. Yeah.
Okay.
Your screen is not visible now.
Okay, sir. Okay, I'm sharing.
Behera sir, kindly share the PPT, sir.
Yeah, sure.
Thank you so much.
And by the time I am opening my screen for the participants, I think many are from mechanical engineering, few are there from polymer engineering. So you can tell me from beginning actually also that whether actually you have some basic things that will already know something about this mechanics, or how we can start the things. And my job for this session, professors actually from all across India, is dual, very clear actually. I'll go for the subject as well as actually I'll do that means to make my department actually visible to all of you. That means what we are doing in my department, that also will be my agenda in between actually. So that if anybody actually need any type of help, we have actually multiple specialists. So you can take the advantage of the things also. Is it... yeah. Whether my slide is visible now, sir?
Yes, visible.
Okay, sir. Thank you. So, okay, friends, actually, as I told, no, participants, you are free to actually to open your things based in your requirement. Sometimes actually I'll mold myself to adjust the situation. So participants, all of you have knows about something about polymer composites, because many are mechanical. For that sake, I'm asking participants.
Behera sir, can you click the word hide? Hide. Hide only. Okay, thank you, Professor.
Participants, you are able to hear me? Is it
Yes, Behera, you are audible.
okay? But all other participants can give your feedback, not issue. So the objective of, because I am in that Indian context of teaching style, so where we used to depend upon actually for our different accreditation process, the course starts like actually what is the my objective of taking this 45 minutes, or and what is the outcome maybe at the end of 45 minutes. Okay, professors. So I'll go through 3 areas within these 45 minutes, 1 hour, to understand the fundamental concept of composite materials, explain the micro mechanics of composites, and correlate these mechanics with the practical application for making polymer composites, particularly to predict the properties. So composite materials are engineered by combining two or more constituents, typically a matrix and a reinforcement, to achieve better mechanical properties that are which are not possible by actually individual. And some friend was asking about actually hybrid composite, and presently I think many are working on hybrid composite to reduce the cost by achieving the target. So the study of these materials for deformation and how the product fail under the different type of loading situations, that is the domain of mechanics of composites. So two things. One is actually that mechanical properties, particularly in a simple word, I will tell actually to talk about stress, strain, elongation, then how the material will fail. In other words, we can correlate that one with actually in our live things, actually how a person can die. That is the thing of actually in failure analysis of any product, we used to do actually that one only. So I may not get that much time actually to go for failure analysis of composites, but because I will constrain myself within the range of actually only in the this deformation part and micromechanics. So as all of you knows, actually the composites, it need two things, minimum two things. One is matrix, the other one is reinforcement. And the matrix may be a polymer, maybe metal or ceramic, but I will constrain myself actually only for polymers. Again, in polymers actually we have two varieties. One is thermoplastic, other one is thermo sets. Then when you go for reinforcement, which provide actually the actual strength and stiffness, that can be in the form of fibers or particles or whiskers. So many already actually those might be joining if they are working on polymer composites for their research work, already might have been acquainted with actually some type of fibers or particles. So yeah. So micromechanics is the study of the behavior of constituents, because when you are making the composite, it consists with actually matrix and fiber. So how they behaves when you are applying some actually external load, study of that one is actually for individual. That means how much the load the matrix will take and how much the load will be taken by the fiber. Study of that one is actually called micromechanics. and useful of predicting the composite properties based on the constituent properties and the volume fraction. So participants, have you heard about actually this? Because I want to little concentrate here, because I came across some papers, but and there are some doubts in actually that meant these fibers. No, we are using actually the reinforcement. We are using in the form of fibers, particles, whiskers, and many times people are using actually the general formula. One mathematical formula is there, actually rule of mixtures. So by using the rule of mixture, if you knows the property of fiber, you knows the property of matrix, then based on your volume fraction of fiber and matrix, you can predict actually what should be the property of the composite what you are going to prepare. So few participants, at least I need few answers. If anybody did any work on polymer composites by using fibers. Whether participants can answer. Professors, anybody did any work on fibers? That meant used reinforcement as a fiber. The glass fiber, carbon fiber, basalt, or any type of fiber. Dinesh, whether participant can unmute themselves and can talk, no?
We can unmute and talk, sir.
Yes, sir.
So please, professors, actually, please, otherwise, actually, the evening will become bored. So please, because many I understood from joined from Gujarat, many are from Kerala, many are from different parts of India. So we Crescentians loves actually these things, and we want to talk actually, because here I am the only, I think, speaker from our Crescent, because who can talk about our actually Crescent, because all others actually they are from different other organizations, because you have a combination of actually industry and other. So professors, anybody did anything, or anybody did on particles? That means any other particle you have added to make any polymer composite?
So we have added carbon fillers.
Carbon fiber.
Carbon black fillers.
Carbon black filler in
Rubber, sir.
Rubber. Okay, fine. Anybody did with actually any thermoplastic material with any filler, either filler or fiber or whisker?
Good evening, sir. Myself Anjali Prakash, Assistant Professor from Central Institute of Petrochemicals Engineering and Technology. So I had done a DRDO-based project, which was development of a polymer composite with epoxy and glass fibers for stealth applications.
Glass fiber with?
Epoxy, sir. Epoxy resin.
Okay, epoxy resin. Fine.
Yeah,
Fine.
for stealth applications.
Okay. Whether you used any type of mechanics to calculate the property?
Yeah, sir. Actually, we had done the compliance standard studies for the thing, but since due to some confidential issues, we had not done extreme things, but we had done all this Laws modulus, storage modulus studies for the thing.
Okay, that okay. Okay. So for all composites, yeah. Any other professor?
Yes, sir. This is Dilip from the MS University, Maharaja Sahadev University of Baroda, and I have been working in the composite field. Previously, I had a group of students who had worked on the pistachio shell composites. What we have done is we used the pistachio shells, and we made the powder of it, and we used epoxy resin as a matrix and pistachio shell as filler. So that also gave us some prominent results.
Okay, okay, fine. So many professors actually you might have worked with actually polymer composites, whether it is actually rubber with some other filler, otherwise actually with a thermoset, like some madam told, actually with epoxy resin, and somebody might have done with actually thermoplastic also. So the thing is, like we used to prepare a composite based on actually that weight fraction, otherwise volume fraction, whatever you are adding. Actually, suppose 90% your matrix, 10% is your filler in the form of fiber or in powder form. Then what is to do actually is to prepare it by using some some method to prepare the composite, because there are so many techniques are there to prepare composites. And after that actually we used to test it. Am I correct? Professors, those who did work, actually I'm asking them. Then after making the composite based actually your ASTM standard, you might have calculated the tensile strength or other strength by using some UTM. But what I am going to tell now actually that before making the composite, itself, theoretically you can calculate what can be the maximum property we can achieve by the adding actually these two type of or three type or five type if you are going for actually hybrid type of composites. So for preparing after making the composites, then we want to find out, for example, what is the Young's modulus. What is the modulus of elasticity? So modulus of elasticity to calculate, I can use actually, there are many mathematical models are there. One of them is actually rule of mixture, but few more are there. But I want to thrust a little bit on rule of mixture, and I'll tell its disadvantage also. Why actually in certain situation you should not use actual rule of mixture to find out the property of the composite. So because this is the simplest one, so many people actually, many works actually people used to do it, and they used to predict the property by using actually this formula. Actually my formula here is EC, stand for actually modulus of elasticity of the composite is equal to volume fraction of fiber multiplied with actually E of fiber plus Vm, where Vm is all you know is actually 1 minus Vf will give you the Vm into E of matrix. Suppose you want to find out the property in the transverse direction, then it is ulta. That means that is called approximate inverse rule of mixture, and in that it's just opposite. Like here actually we are writing EC, there it is 1 by EC, and Vf by EF plus Vm by EM. By that way you can find out the transfer modulus. But anyway, we don't have that much time to go for actual transfers. I am concentrating myself on the longitudinal modulus. That means along the fiber direction, what should be the modulus? So this formula is actually for modulus, but the same thing can be used also for to find out actually the tensile strength of the composite. So the tensile strength of the composite will become V of fiber into sigma of fiber plus Vm multiplied with actually sigma m. Similarly, you can find out density. Anyway, I am taking one case study actually by using this equation, by using actually how you can use. There are actually mathematical tools, actually software also there, and one is actually this. I can use either actually some software like actually this lab view, MATLAB also can be used, and I am showing actually how you can use this, rule of mixture formula in that will be in actually MATLAB. Just a minute. I am showing a lamma. That means how I can predict these properties actually. Particularly, I have 3 examples. One is for modulus, one is for strength, other one is for density. Also, you can find out. How can you use MATLAB? Professor, whether my screen is visible, it is in MATLAB view.
Visible, sir.
Okay. So, like actually, I told no that rule of or by short used to tell that one are actually ROM, rule of mixture. So, actually, all these things I am talking about actually before you are making the composite itself. Whether actually you are going to make that one actually by hand layoff, spray layoff, or whatever the injection molding, compression molding, or any other RTM. Before going for actually making the composite, to know actually what should be the property. So, although by using actually your regular mathematics equation, then you can use your calculator by that way and find out. But what you can do, you can play with actually this MATLAB. Once you create a coding, what will happen actually, because that volume fraction, no, because many of you might have actually did work, might have taken matrix as 90%, 10% fiber or filler, 5%, 10%, 15%, 20%, 25%, 30%, like that you might have plotted a thing. So before I will go for actually those things, how I can find it actually, what will be my optimum volume fraction for that one. So for example, anything, professors, anybody is telling anything? Can I proceed?
Yes, sir. Yes, sir. Proceed, sir.
Okay. So this is actually a coding I have prepared. That is to find out actually what should be the tensile strength of. This is, if you'll see the heading, tensile strength prediction for a polymer composite by using ROM. So the coding is already written. Now, for example, I am taking actually a fiber. Sorry, I am taking a matrix. And maybe my matrix is actually, okay, nylon. So for nylon, I don't know exact value how much. For example, I am putting actually 65 megapascal is the tensile strength of nylon. And I'm using actually some other fiber. So for that fiber, let me assume that this is 400. But anyway, if you'll take some basalt fiber and all, because I did some work with basalt fiber. For basalt fiber, actually the tensile strength is 2800 megapascal. For Rami fiber, for some natural fiber and all, actually you will get within this range 100, 200, 250, 300. So I am not taking any particular material, but if any friend did some work, he will tell me your value, we can calculate here itself. So for the matrix 65 megapascal, and for fiber, suppose I know is actually 400, and I am using actually, for example, 5% volume fraction. Volume fraction 5% means this matrix will become 95, so 0.95, and my volume fraction is 0.05. Okay, professors. So now I want to know for this 5% volume fraction, what should be my tensile strength of the composite. So it is giving the result. So if I am using actually a matrix of 65 megapascal tensile strength, and fiber tensile strength is 400, and my volume fraction 5%, then the expected result is actually 81.75 megapascal will be the tensile strength. I want to find out what will happen for the same one for 10%. Then on that case, this will become 90%. But other things, my fiber and matrix are same. So let me to find out. So it is showing actually if you are 10% you are adding, then actually the tensile strength is 62.5 megapascal. So the earlier value was more than 62.5. This one is actually less than, so that indicate me that somewhere I have to play the game between actually this 5% to 10% of the fiber volume fraction of fiber to achieve what strength I might be needing. Similar thing you can do with, I have one example where matrix Young's modulus is 600 and for fiber it is 2000. I've taken 2800, but you can take your value. And volume fraction of fiber is 0.1. So for matrix it will be 1 minus 0.1, 0.9. I want to know what should be the tensile modulus of the composite. So it is showing around, you will get around 820 megapascal. Or I want to change it. For example, I want to take 20% volume fraction. Then on that case, the matrix will become actually 0.8. And now same matrix and fiber I am using. So for this one, it is coming for 20%, is going higher, 1040. Like this, you might be getting also when you are making some composite by some technique. And after that, actually, you are testing. Then many times we used to show that volume fraction or weight fraction increase. And I got also the modulus has been increased by this much percentage. So these are some of the prediction techniques actually. You can do it before going for actually really making the composite. Similarly, actually I have example for density also. So this coding is made for a density. So matrix density, for example, I took one of my own example. I was working on ABS. For ABS polymer as a matrix and 2.59 is the density of basalt fiber. And suppose my volume fraction is 10% and VM is 0.9. Then what should be the actually density? You can find it out here, 1.2940 gram per centimeter cube. Because always actually when you used to go for polymer composite, we used to go for actually density reduction. So these are some examples of actually how by making coding, and you will go for MATLAB and you can use the values, actually you can play with it to find out to display the result actually well before you will go for actually making the composite. Next is anyway, I'll share this video actually, which is actually I prepared that how to derive that equation. So it is there in and I'll share it. And but now we don't have that much time also to go for the video. So this is regarding rule of mixture and fine. Professor, whether you knows how to find out actual volume fraction? Anybody did work and used actually volume fraction as along your x-axis and because why I am talking about this one actually based on certain cases only I am talking about, because many times we used to go for actually weight fraction. That means 100 gram. In that 100 gram, I will take 95 gram of matrix and 5 gram of fiber, or 90 gram of this one or that one. But that 5 gram what we are talking about, that is not volume fraction, that is a weight fraction. And this equation is actually talking about actually volume fraction. How to calculate volume fraction? Anybody knows, professors? Or I'll tell. My purpose of asking professors all these things actually, if you know me, I want. If you don't know me, then on that case I'll open up.
Sir, weight of volume of matrix plus volume of VC plus VM equal to 1 maximum will get. Is it no, sir?
Yeah, but how to find out VF is equal to how much?
Based on the Halfin-Sa equation. Halfin-Sa equation. By using that, we can able to calculate a volume of matrix plus volume of
No, that's
fiber
fine.
equal to
That's fine,
maximum equal to
professor.
1.
Actually, Halpin-Sa technique, I'll come for that one also, because after this rule of mixture, I'm coming for that one. And when we'll use that one, and when we can use actual rule of mixture to talk that one. But anyway, so this is a formula, professors, actually, to find out actually volume fraction of. Why I'm telling this? Because many times I also did work actually where I have used actually weight fraction. Actually when I prepared a composite, I have taken actually like this 90% of actually, for example, ABS 10 gram of some fiber, but the 10 gram is not volume fraction, because when I'm going to use that actually, whether I'll use that in Halpin-Sa method, otherwise I'll use that one actually rule of mixture method, but I should know actually what is the volume fraction. If the weight fraction is 5%, volume fraction will come actually less than 5% only. Sometime it may be 2 point something, 3 point something, 4 point something, based on density. So if knows mean fine, professors, but if you have any doubt, Halpin-Sa method I will come for that one to predict some other things. So this is a formula actually how you can find out actually volume fraction. What is written on the left hand side, phi f, that indicate actually Vf, what I am using that one in rule of mixture. And the right hand side equation, numerator is this one, weight fraction of your fiber divided by density of fiber, divided by your denominator is all these things. So 1 minus Wf by rho m plus Wf by rho f. Here W stand for actually weight fraction of fiber and matrix, but here anyway it is converted into fiber itself. And rho stand for actually rho f for fiber, rho for matrix. For example, where rho m, all these things. One work I took that example. So the density is actually 1.94 gram per centimeter cube. Density of other one is 1.165. Now how to find out actually the volume fraction? So either use this formula by using calculator, you find out yourself. Otherwise, there is a software also. There is a software. If anybody interested, you can take it. Using CAD fill software, actually, you can directly convert that weight fraction into volume fraction. So no need of our own mind to scratch much and to find out. And we can use it. Can I use for 1 minute? I will show that using CAD fill how you can find out the volume fraction. Professors, based on your answer only, I'll move here.
Totally, how many constraints, professor, in this?
How
Yes,
many
sir. Yes, sir. Please.
Constraints.
didn't get you?
How many constraints?
No, I am talking about only volume fraction. How I can find out? Suppose I am having two material, how I can find out the volume fraction? For example, that's why I am repeating again. I am not using any constant here. I have a matrix. Assume that matrix is actually nylon
Sir,
66.
I have a small doubt. By using the volume of fraction, Vm plus Vc equal to maximum is 1.
Professor, first I should know Vf is how much. Then only I can go for Vf plus Vm.
That I need to calculate for both. How much Vm is and how much Vc is I need to calculate.
No, once
based
I know
on the Poisson ratio, modulus of velocity and modulus of rigidity. 3 things I need. Total 9 constraints. Based on that, I can be able to calculate the volume of fractions and volume of mixtures. Both I can need to calculate.
But you did the work actually for polymers, sir, or for other metric, that means like metals?
Any materials by using the rule of mixtures. And totally it's
rule of mixture is Vf is different actually. This is the way to find out actually, because if I know the two densities itself, actually I can find out. Anyway, I am showing you one example, Professor. I am showing one example how to find out actually simply by knowing the density, how I can convert it into Vf. provided that one with certain assumption with light error here and there. Card field. Okay, professors. So here, no, I want actually, for example, in my case, I am telling. That's why I don't know the others, but to make the composite, I did with actually 3D printing. I did composite with injection molding. I did composite with actually compression molding, and also vacuum infusion. Actually, I've used. So basically, actually, we know actually what is the weight fraction of the things. So now, for example, I know the resin density. So here, resin density meaning is actually that is matrix. For example, I am using actually ABS as my material because recently I did some work on it. So around 1.15 gram per centimeter cube. And I use actually, for example, actually a fiber whose density is around 2.59. Now I want actually what should be the 1.15 and my density is this one. Mass fraction is, for example, 5. Sir, mass fraction, I know the weight fraction only 5. That means I am using 95 gram of matrix and 5 gram of fiber. That is my scenario. And where for the matrix actually the density I know 1.15 either from my literature survey, otherwise I measured myself, and for the fiber also I know. So I want to know now what should be the, for 5% mass fraction, what should be the volume fraction. So the volume fraction is around 2.28. So once I know volume fraction is 2.28, then I can find out actually volume fraction of the matrix. Volume fraction of matrix is 1 minus of this value. So when I will go for actually my rule of mixture formula, when I'll go for rule of mixture formula to find out the property, so to put this VF value and VM value, VM actually will become 1 minus VF. So that I can find out. Professor, you actually somebody got by some other way. Maybe he will share in future also his view so that actually we all will be updated through our knowledge. That is the purpose of this program for 6 days. So many things will learn each other. So this is a paper actually recently I published where it is a hybrid composite, and where I used actually composite mechanics. I use both actually ROM as well as Halpin-Tsai method. So this is example of that MATLAB coding, professors, and now come for Halpin-Tsai model. Professors, those who are working on these polymer composites, if already knows mean fine, and don't know me, this is a general knowledge I'm just sharing. This rule of mixture formula you will use for making a polymer composite, and the fiber what you are using is not a long fiber. For example, you are using short fiber or you are using some filler type of particles. For example, actually you are using some fiber whose length is only 3 mm, 4 mm, and you are going for actually injection molding or compression molding, then definitely that rule of mixture formula will give such a value that it won't actually, when you do the real test, there will be no matching of that one. Maybe real value you will get only 50 megapascal, but your actual value will be this formula will give you actually 500 megapascal. So there are some constraints on rule of mixture. Rule of mixture actually used to give good results only for long fibers, and along the fiber direction it used to give actually good results. Other if you are using actually some other filler, otherwise you are using actually any other type of actually, that means a small type of particles, then definitely actually that I'll show you some result how actually the variation is how much. So this another technique actually, that is next model actually after this rule of mixture. The other one is a Halfin-Sai model. So in Halfin-Sai model actually they used to take actually length and diameter, that means aspect ratio, into consideration. So this thing actually, this one also will height it actually what you will get really. It may not give actually exact value, but it will give little closer compared to actually rule of mixture. That's why many people actually they used to use actually this Halfin-Sai model when particularly you are using actually this small fibers actually. For long fibers you can go for that one, but for small fibers, or you are using some powder, then on that case bring actually the aspect ratio into consideration, where the result may be little actually closer to what you will get actually really. So according to Halfin-Sai model actually, to obtain this one actually, E suffix HT professors is HT for Halfin-Sai model. This is actually, this formula is for modulus, but you can use it for actually tensile strength. You can calculate also density from here. You can find out thermal conductivity also from here. Because recently I saw some GATE questions and all for polymer guys. Actually, they asked about how you can find out actually thermal conductivity based on actually these things. So based on Halfin-Sai model actually, sir, the formula is actually, if you know actually what is the property of the matrix, that is equal to 1 plus this zeta into eta into WF, 1 minus eta into WF. Some people are taking in terms of WF, weight fraction, or some people are taking also in terms of volume fraction. Now, how to find out actually what is that zeta and eta? Eta is the reinforcing efficiency, and this zeta is empirical shape factor. That particularly this zeta take care of your shape of your fiber. And so how to find out actually eta? To find out eta, this is a formula. So this is the modulus of fiber minus modulus of matrix divided by modulus of fiber plus zeta into modulus of matrix. So before getting eta, actually you should find out actually what should be the shape factor. So the shape factor is calculated actually based on actually 2 times ln by d. But if somebody can actually play a little bit actually, whether by multiplying in place of 2 multiply, actually recently I was calculating one value when I did it actually for 10 into n by d, then what happened actually, I got actually the result little more closer what actually I was getting actually by using that Halfin-Sai general method. So somebody can play with it, but the formula which is available in papers actually, it is 2 into ln by d. Ln is the average length of the fiber and d is the fiber diameter. If you are using actually some rectangular shape type of fiber, then on that case this d will be replaced by actually thickness. In other words, actually this ln by d is nothing but actually your aspect ratio. So from here, like rule of mixture, you can create also that meant a coding for this one, and then you can play in your MATLAB to find out actually by increasing, decreasing, all these things. Then since this Halfin-Sai model also, as I am telling, actually there are, it is to give little bit better result compared to the rule of mixture, particularly for short fibers, but still the value is actually very high. compared to the actual values. So there is a modification of Halfin-Tsai model, but the modification of Halfin-Tsai model, professors, the formula looks very small here. Equation number 9, what I wrote. That means this is nothing but actually same rule of mixture, but here actually the additional multiplications are x1 into x2. Although this formula looks actually very simple here, but again to find out that x1 value and x2 value very complicated, because he used actually integration to find out actually the things. So to find out x1, this is the formula, and to find out x2, this is the formula, because here actually your fiber angle also has been taken into account. Because in case of rule of mixture, we are putting the fiber actually straight, and but here actually in reality, when you will make the composite, fibers will make some inclination, so that angle and are also taken into consideration as a factor. So this is called fiber orientation correction factor is x2, and your x1 is the fiber length correction factor. So x1, x2 you have to calculate by using all these mathematics, and then you can do it. But I'll tell another way, because one paper he did actually, because it's very complicated to use now mathematics actually, particularly those who might be actually with a simply polymer background and want to, or if those who are very strong in mathematics also, definitely actually it will take time. So one paper I saw actually where what they did, this is a paper. He used actually this modified Halfin-Tsai model, but not calculated x1 and x2 value actually based on that integration formula. He used take some values actually 1, less than 1, more than 1. That we created a coding, and after that actually played with MATLAB. So finally actually got the results like this. So why I'm telling actually, professors, this rule of mixture, although it is actually popular one, but many times it won't give actually the accurate, it won't give accurate results, because it used to assume so many things, and in reality that won't happen. So in this paper, see this experimental values, professors, is this crossed value, this one, this one, this one. That means the increment happen based on fiber content 5, 10, 15, 20, 25. The tensile strength has been increase. These crossed values are actually experimental. By doing the test in UTM, got the result. These red marks are calculated based on actual rule of mixture, because in this modified Halfin-Tsai model, actually if you take x1 value 1, x2 value 1, then the formula will become actual rule of mixture formula only. So if you take x1 value 1, x2 value 1, then that is rule of mixture. So you see, real value is actually something. Rule of mixture is telling actually more than 100, when actually it has been 10%. Rule of mixture, actually the value is decreased. Actual tensile strength is decreased, which are calculated from experiment. But rule of mixture is telling actually around 200, more than 170, 180. So at 25%, it is around actually you are theoretical reaching somewhere 400, but really thing is not happening that one. That's why I told you actually, because this rule of mixture is based on actually many assumptions, so it won't give the more accurate results. Your accurate values are somewhere, but the result you are getting by using the micromechanics formula rule of mixture is something else. There's so much hype. Then the trial has been made actually based on Halfin-Tsai model, and x1 is not taken 1, x2 value taken 1. Then we got result actually, at least it is not actually coinciding, but at least it is lesser than actually that x1 1, x2 1. That means compared to rule of mixture, it is coming closer at least towards actually your experimental value. Then proposed model they did actually with x1 is equal to 1, x2 greater, not equal to 1 means they took actually 0 point something. And the third trial is made, last trial made actually with the proposed model. Both x1, x2 values actually with 0 point something. That will be in between 0 and 1. They got actually these values, these red circles. Those are actually the fifth one, proposed model x1 not equal to 1, x2 not equal to equation 21. So it is giving actually much more closer. Same thing is happening in case of actually your Young's modulus. See, the red one, no, that rule of mixture is giving so high p values, but real values are actually something. So in short, I want to tell actually that when for long fibers, you are using hand layup or spray layup technique, then on that case may actually, but still, because in hand layup and spray layup technique, you manually you are doing, you don't have many controls. So on that case also variation will be there, but still those things actually little closer. But if you are going for actually any type of whiskers, we are going for actually short fibers or any other type of fillers, then on that case actually that Halpin-Sai model actually used to give actually little better result compared to so time is already 8:10, but can I talk about 5 minutes about a case study with the permission of
Yes, sir. Yes.
Can I go, professors? Okay. So professors, just concentrate, because I have taken a case study where actually we are using this micromechanics concept to find out. That means these are the design stage of the composite actually what you can do. So the scenario is, it is desired to design one tensile member made of a unidirectional composite material. This unidirectional, professors, I am repeating again that rule of mixture will give actually good result. That means if the fibers are actually aligned in one axis only, then along that axis actually it will give actually, and the values actually what you will get from rule of mixture almost very closer to actually the experimental value. The structure is to carry. That means this is a case study I took actually where actually some other component has to be replaced by using actually a polymer composite in some automobile. So 2200 Newton load, axial load has to be taken. The length should be 3 meter. Cross section is circular. The matrix is because many of you might have done work with actually epoxy. So knowingly I took actually epoxy, but you can play with my same case study. Actually, you can go for other type of matrix and you can do the things. And the yield strength for this one is actually 80 megapascal. But when you are doing actually the real thing, actually when you are getting your epoxy material from your supplier, you can get that value from them. The yield strength of the composite, these are the conditions actually. The composite should not exceed the yield strength of the epoxy. That means the composite what you will make, its yield strength should not be less than 80 at least. This is to make sure that if the fiber breaks by chance because of something, the epoxy itself will be able to take the load without any catastrophic failure. Assume a modulus of 3.5 gigapascal for epoxy and require that the composite member should not stretch more than 2.5 millimeter. Those who might be teaching strength of material, many of these, or those who might be actually mechanical design also, you know actually there are constraints. There will be constraints. You have to do your design actually within that. So the elongation should not be more than 2.5 mm. Now you have to design the things. But for this one, some other information also that like you used to use, design data book. So here I have a table from where I have to select the fiber and all. So once I'll proceed forward, I'll tell you. Professor, to do this exercise, I have this table. From here actually I'll choose. I am telling you the steps. So repeating again, professors, because without remembering this one, when I'm proceeding further, that will be violation actually. So I have to design a member. It has to carry a tensile load 2200 Newton. Its length should be around 3 meter and made from epoxy. and some fiber. That fiber you have to choose. Only for epoxy matrix, actually, they have given the data. The other condition is actually if by chance, whatever the fiber you are choosing, by chance during the end use application, your fiber breaks, no problem. At least the composite should be able to take that load only by the help of your matrix. And the elongation should not be more than 2.5 mm. So professors were to do how to start this. So first what I did actually, I assumed that I am going to make a composite, not the combination of actually matrix and fiber. It is only made from epoxy. So if I assumed that entirely made from epoxy without any fiber, then what could be the maximum strain? So the maximum strain is change in length. I've used actually our strength of material formulas. So change in length by original length. So by that way, I got actually the maximum strain. That means maximum strain is 0.88 into 10 power minus 3. So once I know actually maximum strain, I can find out actually stress. How much maximum stress will induce. So this multiplication of strain and your Young's modulus, that will give actually me what is the stress by simple that Hooke's law. So the strain is actually 0.88 10 power minus 3 multiplied with 3.5 into 10 power 9, because here it is given the modulus of epoxy is 3.5 gigapascal. So I have converted that gigapascal into Pascal. So multiplied that 10 per 9. So find out, got it actually, the maximum stress. If I make this composite actually, this particular product only from epoxy, then the stress will be actually 2.92 into 10 power 6, or you can say 2.92 megapascal. Now let me to find out actually, because now keep in mind professors, I'm using only matrix, no fiber. So simply actually if I'm making the product only by the help of actually matrix, then from my calculation I got the area load by stress. So that gave me some value, and finally actually that area is equal to pi by 4d, because it is a circular section. So the area is equal to pi by 4 diameter square. By that way I got actually diameter. So the diameter is coming 31 millimeter. That means if I'll make this particular product which will carry 2200 Newton load, elongation will not exceed 25 mm, and it will be made only from epoxy, then the diameter requirement is minimum 31 millimeters required. Less than 31 millimeter, the product will fail when you will apply 2200 Newton. So either 31 or more than 31, you have to go for. Okay, so I got an estimation that if I'll not go for actually fiber matrix together, then the diameter of the product is requirement actually is 31 mm. Now the mass density of epoxy, actually density of epoxy, professor, in that case study I have not given, but if you will see your papers, actually epoxy density lies between 1050 to 1300 kg per meter cube. So approximately I took a value, but you can do the calculation by taking your, if you know the exact value. So I took the density is equal to, for epoxy, 1250 kg per meter cube. So once I know the density, I have calculated the mass of the tensile member, which is only made from epoxy, by multiplying the density with volume, and because the length is 3 meter and this is my area into length becomes your volume, and this is density. So approximately 2.83 kg of material is required. My purpose of doing things, professors, because when you are going for actually polymer composites, when you will go, you people might be actually teaching in your class also advantages of polymer composites or polymeric material, low weight, good mileage will give actually in that means in case of automobile. Then on that case, actually, this weight reduction is actually the important criteria when you are going for actually this type of things. Because of that, actually, I have calculated if I'll do it actually only from epoxy, how much kg. So around 2.83, because finally I'll compare this value with the composite, what we'll make with the fiber with the matrix. So the minimum modulus of the composite is equal to, for this composite from epoxy, is maximum yield strength divided by maximum permeable strength. By that way, I got it actually 96.4 gigapascal. That means if the modulus of this composite will be less than 96.4 gigapascal, professors, it will fail only. So minimum requirement is actually 96.4 gigapascal. Then if this is your requirement, whenever you are going for actually making composites, adding, you can add more than 2 material also, professor. That is hybrid. I'm not going for that. I'm talking about only 2 material. One is fiber, one is matrix. So when you draw your stress strain diagram, suppose for example for matrix, this is the stress strain diagram, and for fiber alone, this is the stress strain diagram. This is for fiber and this is for matrix. And when you will make a composite, the property of the composite will lie between actually this area only. It will not become less than actually your matrix value, or it will not become actually more than the fiber value. It will lie in between actually. That's why, since my composite, for that composite, I need actually minimum requirement of modulus 96.4 gigapascal, and the matrix is fixed. Actually, I can play with actually only fiber. Matrix is fixed. Matrix is actually epoxy. I cannot change that. So matrix is only 3.5 gigapascal. So now to achieve the modulus 96.4 gigapascal, professors, from 3.5 to 96.4 gigapascal, definitely you need some fiber whose strength, whose modulus value should be more than actually 96.4. Simply 96.4 by maybe 100, 120, 30 also will not, you cannot achieve. So definitely you have to go for actually very high modulus for fiber. Now next step is you are going to choose actually the fiber, because only matrix is fixed. So definitely a composite of this type will have a modulus not less than okay. As per the information, when 2200 Newton load will be applied, with the fiber breaks, then the epoxy alone. I left one. Okay, professor. I left one slide actually. That's it. So now actually first I have to choose actually what should be my fiber. So for composite I need actually 96.4 gigapascal, and my matrix modulus is only 3.5 gigapascal. So now I have to choose some value. I have to choose some fiber whose modulus should be high, sufficiently higher than 96.4 gigapascal. Then only it will work. I can achieve 96.4 gigapascal. So for choosing, although here I took a small table only, professors, for just to do this, but you have actually for all materials you can gather actually what should be their, what is their elastic modulus, what is their tensile strength, all these things. So let us in this small example actually let us, I will try. For example, professors, I'll choose E glass. What is the modulus of E glass? Professors all are active, no? Because already 8:30.
72, yes.
Yeah. So professors, actually I cannot choose actually E glass. The reason is the composite what I want, its value minimum requirement is 96.4 gigapascal. If I'll take my fiber as E glass, whose E value only 72.4, my matrix is 3.5, and I'll make a composite, maybe I'll get actually E value around 20 or 29, 31, 35 gigapascal. So definitely I cannot. That means other what I am telling, less than 96.4 value of elasticity modulus of fiber will not work. So all these glass fibers, none of them will work. All these values are less. Okay, in polymer, Kevlar is there 124, but any professor you can calculate, because I'll share these things. You can try yourself because I have not tried for that. 172, but according to my experience, without calculating, have an idea that if I'll go for actually 124, 172, and my matrix is only 3.5, definitely actually it won't be possible. May be possible, but in that case my fiber volume fraction of fiber will show me from calculation 0.96. By using actually 96% fiber and only 4% actually matrix, I cannot make actually, while preparing the composite, I cannot do that. That is actually during manufacturing also some constraints are there. So, okay, professors, you can do your work. What I did knowingly, actually, I took highest value. I choose actually carbon fiber with high modulus. Carbon fiber, there are two. One is high strength, other is high modulus. Because the comparison I'm making for high modulus, so I took actually this one. I have chosen actually carbon fiber, and its E value is actually 531. So the selection with that. So from the table I got actually, I went for high modulus carbon fiber, whose density available in the table, and the elastic modulus is 531 gigapascal. So since now I know actually the E value of matrix 3.5 gigapascal, E value of fiber, what I have chosen now, 531 gigapascal. Now I am in, and I know actually my minimum requirement is 96.4 gigapascal. So what I did, I use now ROM, rule of mixture. So Young's modulus of the composite is equal to volume fraction into EF plus volume fraction of matrix, which is I wrote in the form of 1 minus VF. Like one professor told, actually VF plus VM is always 1 only, into E of matrix. So my requirement is 96.4. Volume fraction I am going to calculate, and EF for fiber actually it is 531, and for matrix it is actually epoxy resin. Its E value is 3.5 gigapascal. So after solution, professors, I got actually volume fraction minimum requirement is 0.176. That means 17.6% of volume, in terms of volume, fiber I need to achieve this Young's modulus. If it is more than fine, you will go more than 96.4. But minimum requirement is 17.6. So for 17.6, the matrix volume fraction of matrix, it will be 1 minus 0.176, so it is 0.824. So by this way I got it actually, what should be my volume fraction of fiber requirement. Another 2 minutes, professor, already time crossed, but still I'm finishing. So definitely a composite this style will have a modulus not less than 96. As per information, when the load will be 2200 Newton load applied, just recall, professor, there is a sentence in that question itself. If the fibers by chance fail because of something, at least your matrix should be able to carry the load. So like actually mechanical guys might have knows, whenever actually suppose at least one gear fell, at least the other should work to reach some safer place so that actually the repair can be done. Otherwise, the recent example of that aeroplane also, because everybody told actually both the engines failed, at least one might have active, might be okay, at least the pilot could have actually landed it safely. So here the situation actually, I am going to take care of things. At least if the fiber actually will fail, then the matrix itself actually will be able to take the load. So if the fibers break. So now what to do actually, what I did here, I have equated actually the load is equal to stress into area. So load is equal to stress. Load is 2200 Newton. Stress, this is I am from actually. I am checking now if by chance the fiber fell, then matrix itself able to take that 2200. So for this one is given, I think 80 megapascal given data, and the total area, because I am taking only actually volume fraction of the matrix is actually 0.824. So 0.824 of the area, because when you compare volume, the length will be cancelled. So that area will be whatever the volume fraction of matrix, that one you have to multiply here. So by multiplying this one, professor, so we got actually the area is first I got in meter square, but converted into millimeter, 33.33 millimeter square. And this one equated again pi by 4 d square. So diameter of the thing came actually 6.5 mm. Again we compared actually volume and again find out the mass of the composite. But mass of the composite I got actually from the, again, rule of mixture. This is the density, professor, for fiber 1900. This one is VF plus density of resin, actually that epoxy resin 1250, and its VM is 0.824. All these things actually, this is totally actually total volume of, sorry, density of the composite multiplied with density with actually volume. So the volume actually here I have calculated 10 power minus 4. Sorry, it is not meter square, it is meter cube actually, sorry. So by that way, professors, we got actually mass of the composite. That means by taking actually 0.824% of, sorry, 82.4% of actually matrix, 17.6% of actually fiber, and particular fiber is actually we have taken carbon fiber with high modulus. Then the mass or weight is actually only coming 0.137 kg. So when I'll compare actually, when I calculated actually that simply from epoxy I made actually I was needing 2.83 kg, but by adding this fiber and all actually we are getting 0.137 kg. So there is a huge mass reduction, almost all actually from 2.83 divided by 0.137. I think it is coming around 119 or 120th reduction is happening, and diameter of the composite reduced from 31 to 6.5 millimeter. So this is a case study, professor. Then like actually in our first speaker was talking about actually specific modulus, specific strength. Particularly specific strength, specific modulus are important terminologies to calculate, to make a proof that your composite is actually lighter in weight. So that actually what will happen, if you will use it in case of actually simply tensile strength will not talk, because when you are going to calculate specific tensile strength or you are going to calculate specific tensile modulus, that will tell actually for 1 kg of material what is your strength, 1 kg of material what is your modulus. So when you are going for actually comparison of actually that weight reduction, particularly in case of automobiles, or although my work is not on aerospace, but the terminology is common actually. So those are the things actually, in place of simply calculating actually tensile strength and modulus, better calculate actually specific values, so that through that you can make a proof that the weight has been reduced. I have one more case study, professor. This one is actually one metal has been replaced by a polymer composite, but shortage of time, so excuse me. Hopefully I'm completing here because already I exceed the time limit.
Sir,
Just a minute, professor. Okay, you can open your videos also, so we can see each other, not an issue. Dinesh, so from my side, actually, for this session over, although I have few more case studies, but no much time. So now,
Thank you for your valuable insights, sir, and for sharing your valuable knowledge on a volume fraction of fiber and matrix to calculation in the manufacture of composite materials, sir. So, there is some question posted in the chat box by the participant, Avinash. Did you see that, sir? Shall I read?
1 minute.
Avinash from Hindustan University, Chennai.
Can you read?
Yes, sir, I'll read, sir. So, in case of multi-axial fabric, like quadriaxial fabric, how do you account the varying fiber orientation while applying the rule of mixture to predict the tensile property?
Actually, Professor, you cannot use actually this rule of mixture. This is a simple formula only for that complication of the things. If you need, actually, I can send you some, because you have to go for actually that theories of failures formulas, where actually you have to use actually, because by using that matrix and all, actually you can find it out. And I don't know what books and all you are following, either see some papers, Professor. Otherwise, actually, if my phone number is there, if you need anything, actually, I can share you how to go for those type of situations. Because here I didn't bring actually those complicated equations. The reason is actually here people are actually from multi disciplines are there. So because of actually I went only for that simplest one, but based on requirement, actually you can go for actually that different failure mechanisms are there, no. So how to find out actually the stress in along the one direction, two direction, two direction. Okay. So please, actually, I cannot answer that actually here, Professor, but you can contact some other time. You can. Not an issue.
Any other questions? Yes, sir. Yes, please.
Professor.
Yeah, send me, sir.
Professor, in case of, I don't know whether it's a right or wrong. In the case of fiber, in unidirectional, bidirectional, both directions are there, no? In the unidirectional, by using the Alfvén-Say equations, how many constants to be calculated in case of isotropic or anisotropic or orthotropic it is? For the same cases, if it is the bidirectional.
Okay.
In that cases, if I go for anisotropic, how many constants to be calculated? I mean, for the warp direction as well as for the wave directions.
No, because in that formula, what I shown, Professor, X1 and X2 only they are doing, because that is actually, it is only for single fiber. But as you are talking about actually multi fibers, I don't have the idea of actually what are the other factors has to be multiplied actually, because on that case actually both thing has to be taken into account, Professor. I didn't actually,
because Professor, is there any method for the uniform distributions of the fiber? Is there any method, exact method?
Yeah, Professor, actually either you can do those things at the same time, but one method actually, one paper also I published actually, where to find the uniformity I went for actually Cole plot. There is a plot,
Cole plot.
Cole plot. That one can be done through actually from your result of DMA analysis. You are having, because in case of
Professor, I have seen it during the analysis, they are asking all the constants it is.
No, Professor, I
So
don't
there
have
is a three method of analysis over there. So that's why I asked you, Professor.
Okay, no problem. One method, Professor, actually I want to share. There is a method of for seeing actually uniformity of your fiber as well as fillers from the result of DMA by plotting Cole plot.
Okay, Professor. Let me check.
Yeah, please.
Thank you, Professor. Thank you.
Yeah. Everything I cannot, Professors. I have some limited things, and
thank you.
Whatever knows actually I can share, and later on also you can talk. And our department of Polymer engineering is free to actually make your things if anybody actually working on composites. And
what is the trending, Professor, in composites? Recent trends.
Go for hybrid composite to make the cost calculation, Professor.
Hybrid.
Yeah, because somebody was asking, in first speaker. For example, one work I'm telling, one work. Suppose I am using only, that is my own work. I am using only ABS.
Okay.
ABS is a polymer in many of the car company they are using.
Okay.
Only carbonate ABS you might have heard about these polymers. So these are some common.
What's your opinion about? What's your opinion about natural fiber, Professor?
Yeah, you can try with natural fibers, Professor, because the cost will be reduced, provided actually the other things actually not compromised. Properties are not compromised.
Yes. Okay, Professor. Okay, thank you, Professor.
Okay, sir. Thank you. Okay, so already we exceed, I think, 8:30 today. So excuse me for because I took some 10-15 minutes extra, but in tomorrow's session and all, actually we'll try to finish it within the time, Professor. Okay, and if anybody actually, as we have created that group, and if anything, professors, you just all of you are free to make the things. We'll try our level best. Our team will try our level best to help you actually. What was? And just to inform you, 1 minute I'll take extra. Whatever the help, suppose somebody need professors for making composites, for analyzing things, or whatever the knowledge we have, our faculty in the Department of Polymer Engineering, we can do that. And if any other thing actually you can share in that actually our group what we have created. And if any of your friends not joined, because some of the mail what happened actually it bounced back to me. So because of that, actually few people I think not joined. So if not somebody not joined, sir, tell them to contact me directly so that we can make the issue. Okay, thank you, Professor HOD Polymer Engineering, Madam, Dr. Majid, sir, and Dean Mechanical, and our Dr. Mahesh, sir, from Aerospace, as well as our young faculty from Aerospace, Dinesh, for making the session today. That meant because it is a 6-day program, so I think we have to go forward.
Thank you, sir. Thank you for the valuable inputs. I hope the session will be more interactive and the informative session for the participants. Thank you, sir.
Okay, sir. So